This video will be about transforming parabolas. So a parabola is the representation of a quadratic as a graph. So we have y equals x squared, that's our basic function, also known as the parent graph. So the parent graph we could find making a table. I already know what the points are, so I know there's a point at 0, 0, 1, 1, and 2, 4, negative 1, 1, and negative 2, 4. So if you know this parent graph, you can graph any other parabola as long as the equation is in vertex form. So this is our vertex form. So when it's in vertex form, each different letter, A, H, and K, will represent something we can do to the parent graph. For example, maybe slide the parent graph around to the right or slide it to the left. Maybe it'll slide it up or down, or it may stretch or shrink the parent graph or flip the graph upside down. So we have a lot of different options that can happen knowing that vertex form. So to give myself a little more room, I'm going to rewrite the vertex form here and talk about what each letter does. So first, H will move the graph left or right. To know if you're going left, the number actually has to be positive. So this whole thing, if we had x plus 5, that actually means move left. So left is positive. To go right, we'd do the opposite, negative number. If that said x minus 3, that would mean move right 3. Second is K. K will tell us to move the graph up and down. This time, up will be positive, and down will be negative. If you had plus 5, we'd be moving up 5, and if you had minus 3 at the end, it'd be down 3. So the last letter is this letter A, and it serves two purposes. It says whether the graph is opening up or opening down. So if A is greater than 0, the graph opens up, meaning it looks kind of like that U shape. If A is negative, if it's less than 0, the graph opens down. Which means it would be upside down. The second thing A can tell you is if your graph is going to be the same width as the parent function, or if it will be wider or narrower. If A is between 0 and 1, and I should say the absolute value of A, meaning we basically ignore if it's positive or negative for this second piece that it tells us. So if A is a fraction that's smaller than 1, then that means the graph will be wider. If the absolute value of A is bigger than 1, the graph is narrower. So looking back up at that parent function, when I say wider and narrower, wider would mean kind of move the sides out and down a little bit, and it makes it wider. If we were talking about narrower, it would move it in a little bit. So let's try graphing this function. Y equals negative 2 times x minus 1 plus 3, x minus 1 squared plus 3. So looking at what each number tells us, we have a negative 1 inside here. We said negative actually tells us to go to the right, so we have to go right 1. 3 is positive, and we're going, so we go up 3. Since it's positive, it's moving our graph up. A in front is negative 2. So the negative tells us that we're opening down. And the 2 will tell us that we are getting narrower. So the parent graph is where we start from. Our parent graph looks like that. Then we want to take that parent graph and move the whole thing right 1 and up 3. So I can actually drag this around and show you right 1, up 3. But if you don't have, the capability of doing something like that, we've got to just count. So each point would be going right 1, up 3. Right 1 space, up 3. Right 1 space, up 3. Right 1 space, up 3. So we'd have to literally just count from each point to take our graph right 1 space, then up 3. But we're not done yet because we still have to figure out, well, how's A going to affect it? So we know it opens down. Every point would be flipped upside down. So instead of going up, we'd have to go down. Instead of going up, we went down. And then there's one more thing that A can do to the graph. It's going to make this narrower. So when we are deciding, well, how narrow is it going to get? Looking at our points, we went down 1 and over 1. So we went down 1 space, over 1 space. Kind of like a slope from when you were graphing basic lines. The 2 is going to make you go down twice as far. So instead of going down 1, I'm going to go down 2 over 1. So now we look at the other point. We have to go down 1, left 1 to get to the next point. But it's going to make us go down twice as far, or if we had been opening up, the number in front would make us go up twice as far. So down 2, left 1. Here we go down 4, right 2. But we have to go twice as far, so down 8, right 2. Down 8, left 2. And that gives us a graph that is narrower. So the purple is our final answer. I'm going to draw it separate from all of our different steps. Just going to get rid of that. I need to have that there. So here's just our final graph on its own. So looking at this final graph, we can get some information on this final graph. First, we can find the vertex. The vertex is either the topmost point on a parabola or the bottommost point. This vertex would be 1, 3. Second, we could write in the line that's called the axis of symmetry. The axis of symmetry is the vertical line that cuts the parabola in half. Now, vertical lines always start out as x equals. If it starts out y equals a number, it would be horizontal, but we want vertical, so we do x equals. And we want to know, where did that vertical line cross the x-axis? Well, it crosses at +1. So x equals 1 is our axis of symmetry. You can also figure that out by looking at the x-coordinate of the vertex. The x-coordinate of the vertex is the same number that you would use in the axis of symmetry. Finally, we could also talk about the y-intercept. That's where the function crosses the y-axis. So when that happens, we know x is going to be 0, and then on this particular picture, we cross at 1. Now, if you don't have a picture, you could find the y-intercept just by plugging in 0 for the letter x and simplifying until you get one number. So there can be some variations on how they ask questions. So they may ask you to write an equation given the vertex and another point. So to write the equation, we're going to have to go back to that vertex form. Now the vertex is the h and the k parts. The vertex, the x value of the vertex is h, and the y value is k. So we can go plug that in right away. X minus 3 plus 4. Now the point is used to help figure out what a equals. We know every point is x comma y, so we're going to replace y with negative 4 and x with positive 5. So 5 minus 3 gives us just 2. We're going to minus this 4 from both sides. We get negative 8 equals a times 2 squared is positive 4. And then to get a completely alone, we would divide both sides by positive 4. So then our final answer would be y equals negative 2 times x minus 3 squared plus 4. The last variation that they might show and might ask you questions on is if you're in standard form. Say we have y equals 2x squared plus 10x plus 7. And we want to find the vertex and then write in standard form. So find the vertex first. To find the vertex when you are in standard form, we have to use the formula x equals negative b over 2a. That formula will give you the x-coordinate of the vertex every time. So when we're looking at a quadratic, the number in front of x squared is a, number in front of x is b, and the last number is c. So we need to plug this in. Negative b is 10, divided by 2a. 2 times 2 is 4. So negative 10 over 4, when we divide that, we're going to get a decimal, negative 2.5. So now, we need to find the y-coordinate of the vertex. To find a y-coordinate, we're going to plug in the x-coordinate we found everywhere we see the letter x. So we would have to now go plug all of this into a calculator. That gives us negative 5.5. So now I would like to write this in vertex form. Now we actually already know what a is because a is always that number in front of x squared. So we use the same a even if it's written in vertex form. So then the formula said x minus the x-coordinate. Our x-coordinate is negative 2.5 plus the k, which is negative 5.5. So we simplify, a negative negative makes it a positive 2.5, and a positive negative makes it a negative 5.5. So now this is written in standard form. So that concludes our discussion of transforming parabolas.